Hello everyone, I'm Akanksha Sneh along with my colleague Akanksha Tewari from IIIT Delhi. We are grateful to the Qualcomm team for mentoring us in our project titled Hardware Software Prototype of IEEE 802.11ad AY Joint Radar Communication Transceiver. Akanksha and I are pursuing PhD from IIIT Delhi. The faculty members of our team are Dr. Shobha Sundaram and Dr. Sumit Darak. Here is the outline for our presentation. The main goal for the next generation intelligent transportation system is to increase road safety, reduce road congestion, and ensure mobility for all. V2X communication have been identified as a key enabling technology for ITS. One main goal for V2X communication is the sharing of 3D environment sensing information, which demands a high data rate of the order of Gbps and latencies below 1 millisecond. Unfortunately, the state-of-the-art V2V communication technologies operate at sub-6 GHz carrier frequencies. These technologies only support data rate of the order of Mbps and latencies above 10 milliseconds. Millimeter wave has been identified as a viable approach for V2X communication, and it offers unlicensed spectrum and can support higher bandwidths with Gbps data rates. But millimeter wave has some limitations. These links experience very high propagation loss due to atmospheric absorption. Thus, they are meant to operate in short-range line-of-sight conditions with rapid beam alignment. There are several approaches in the literature for rapid beam alignment, but have some drawbacks such as increased latency, interference issues, extra hardware cost, etc. The main contribution of our work with respect to the state-of-the-art is the implementation of radar functionality within the communication framework to enable rapid beam alignment required for millimeter wave communication. Prior art has extensively studied the cohabitation of Comm and radar system on a common spectrum. There can be different scenarios. The third scenario is the one which we are focusing in our work, where both localization and communication are integrated on the same hardware and same waveform. Based on the limitations of the state-of-the-art, our key objectives are the following. First is proposed 802.11ad AY JRC architecture. Second is the develop radar signal processing algorithms. Then develop complete end-to-end software prototype of IEEE 802.11ad based JRC transceiver. Develops hardware-software co-design based reconfigurable RSP for JRC. And develop complete end-to-end hardware prototype of JRC transceiver on heterogeneous system on chip. And finally, evaluate performance analysis of radar operating metrics and communication link metrics. We will begin with the timing analysis for the beam alignment in standard architecture. Here, an in-packet search method is used to determine the best beam pair between the base station and the mobile user. Firstly, the different packets are sent with optional training fields, each corresponding to a beam in a different direction, and are received by mobile user one by one through different beams, which are then processed sequentially, and then the best beam pair is obtained through correlation. Then the uplink is sent to BS receiver with the feedback for the best beam to be sent by the BS. This uplink is further processed at the BS. This completes the stage 1, where BS and MU both know their best beam. This takes approximately 80.1 milliseconds. Now coming to our proposed architecture, where only the radar waveform part of the preamble is sent at the start. The radar waveform is followed by omnidirectional downlink packets sent from the base station to the mobile user. The radar echoes reflected by the mobile user will be gathered by the BS after two-way propagation. The downlink pilots will also be received by the MU through different beams. Best beam with the highest gain is obtained for MU and will subsequently send the directional uplink coming from the mobile user and the coming from the mobile user. At the BS receiver, Comm radar detection unit separates the uplink and the DL radar echoes. Now these radar echoes go through RSP and localize the target. This information is used by the base station transmitter to send directional beams. This stage 1 takes up to 20.1 milliseconds. Thus, we can see that our architecture completes the stage 1 process in a very short time as compared to the standard. In this slide, the RSP algorithm has been explained in detail. The input to the RSP block is the 3D radar data cube of multiple targets. The 3 dimensions of the data cube are first time samples of comprising of number of samples within one frame, the slow time samples across multiple packets, and data from multiple antenna elements. This input goes through the match filter and 1D FFT, which gives output as range and azimuth of the target of the highest peak. In order to detect multiple targets, we use clean algorithm. After getting the range and azimuth information for all targets, we process the corresponding indices across all the packets for Doppler estimation of each target using music algorithm. Here we discuss the trajectory and target modeling. We have considered 3 types of targets in our work: a point scatterer, a pedestrian, and a mid-sized car. The view graphs correspond to the 2D range azimuth plots for each target respectively. We have considered 2 types of trajectory, radial and tangential. Next, we present the performance analysis of radar metrics, where we measure the accuracy of the localization of target in terms of RMSE for range, azimuth, and Doppler velocity. The results have been obtained for single and multiple point targets and have also been benchmarked with the FMCW waveform, which are commonly used in millimeter wave radars. In these following view graphs, we observe that RMSE for range, azimuth, and Doppler decrease with the increase in SNR. Results have been obtained for different channel conditions, which include free space and Rician channel. RMSE in Rician channel is higher than that of the free space due to higher attenuation. Similar results have been generated for the extended targets, which include pedestrian and mid-sized cars. Here, the RMSE is higher as compared to the point scatterer, as extended targets are spatially larger. Next, we present the performance analysis of communication metrics. First, we discuss the radial trajectory under free space condition and calculate BER for a duration of 0.2 and 1 second respectively. We observe that as soon as stage 1 is completed, MU remains in the beam for the rest of the time. Also, stage 1 is completed earlier in both versions of JRC as compared to the standard. Similar results have been generated under Rician channel, where we observe that BER is slightly higher in stage 1 as compared to free space. Next, we consider the tangential trajectory of mobile user. Here, as soon as MU gets out of the beam, stage 1 process starts again. Still, JRC versions have lower latencies for realignment as compared to the standard. We also have done the throughput comparison of the 3 architectures for different trajectories and channel conditions. We have carried out the simulations for multiple mobile users as well. We have considered 2 mobile users undergoing different types of motions. In the first scenario, the mobile users move radially with respect to JRC, where we consider 3 scenarios. In the first one, moving in the same direction. In the second one, MU moves away while MU2 moves towards the BS. In the third, MU1 moves towards and MU2 moves away from the BS. We obtained BER with respect to number of packets for standard and JRC for each mobile user. SNR plots have also been added for exposition. In each of the view graphs, we can observe that the BER is higher for more packets in standard as compared to JRC. Similar results have been generated for the tangential of the both mobile users with respect to JRC.
Slide shows a preliminary demonstration of JRC on FPGA. The hardware IPs for the base station transmitter, receiver, and RSP5 have been developed by Simulink. The FPGA in loop flow is used to offload some of the tasks from MATLAB to the FPGA. In the first video, only the base station transmitter is on FPGA and the remaining system in MATLAB. In the second video, only RSP is on FPGA. We have developed a reconfigurable architecture with three-dimensional RSP capability for multiple targets on an edge platform, Zinc MPSoC. Xilinx AMD multiprocessor system on chip comprises of a quad-core E53 ARM processor and an ultra-scale FPGA. We use the hardware-software co-design approach for the implementation of RSP, where we partition all the tasks between processing system, PS or ARM processor, and programmable logic, PL or FPGA. Tasks such as 802.11ad waveform generation, target model, wireless channel, and clean algorithm are conducted in PS. And since these tasks are sequential and require large amount of data generation, the match filter and music block have been implemented in PL for high-speed parallel processing. The data transfer between PS and PL takes place through direct memory access. MPSoC supports the runtime reconfiguration capability, which allows the hardware to reconfigure on the fly based on the control information sent by the PS. MPSoC also supports a display unit which is used to visualize the results after performance analysis. This video shows the real-time demonstration of RSP and a GUI developed on MPSoC. The user can select the number of targets, target parameters, word length, SNR, and based upon the selection, the radar received signal is generated, the hardware RSP IPs are called, and the results are displayed. Here we discuss the complexity and performance results of RSP on MPSoC. We've explored different hardware-software co-design configurations. In the first one, we have all the RSP blocks, range, azimuth, and Doppler velocity blocks in PS. And since the FPGA is not involved, the acceleration factor is 1. In the next configuration, we shift the music block to PL. This gives a very slight acceleration, but very large resource utilization. Now we shift the match filter block to PL. It gives a higher acceleration factor as compared to the first configuration. On keeping all the blocks in PL, the acceleration factor further increases, but at the cost of very high resource utilization due to single precision floating point architecture in hardware. Thus, we use a fixed point architecture with 24-bit word length, which provides up to 40 to 70% reduction in resources and an acceleration factor of 120. The RMSE plots below show the functional correctness of this fixed point architecture as compared to floating point. Lastly, we use a serial parallel processing implementation of match filtering with fixed point architecture with 2 parallel azimuth processing blocks for the highest acceleration factor. Here we demonstrate the runtime reconfiguration offered by our hardware IPs. Based on performance and complexity requirements, we can on-the-fly switch between different parameters, such as different number of packets and Doppler resolution in the music IP, and different azimuth precisions in the match filter IP. These parameters offer an accuracy versus latency trade-off. Here are the project outcomes that we have completed within 1 year, and these are some of the published works related to the project. In the future, on the algorithmic level, we plan to incorporate JRC with multi-armed Bandit and propose 2 frameworks. First is the amplitude-gated radar enhanced map, where we select the number of beams based on the presence of target. The other is the Doppler-gated radar enhanced map, where beams are selected based on the presence of mobile target. Here, the tasks that are completed are shown in the green box, and the tasks in the red box are yet to be completed. In the architectural level, we plan to optimize the RSP so as to get an even higher acceleration factor on hardware. The first approach is to develop the hardware IP for the clean block, which is currently performed on ARM processor. This would offload the complete RSP to the FPGA and reduce the PS to PL data transfer overhead. In addition to this, we have identified some redundant cross-correlation operations in the RSP, and we'll accordingly optimize the hardware IPs for higher acceleration. We'll explore the scope of dynamic partial reconfiguration in our design so as to offer significant savings in area and power. Based on the channel SNR and clutter conditions in the environment, we can enable averaging across a number of pulses for better target estimation, and this parameter is known as the integration factor, which can be made reconfigurable. Also, we can select different opto processing blocks as per requirement. For example, music can operate on a lower number of packets, but has high complexity on hardware, whereas FFT, which offers low complexity, but requires larger number of packets. In future, we plan to build a system-level design for JRC transceiver by integrating all the hardware IPs on heterogeneous SoC and analyze the performance of system in terms of communication link metrics and radar operating metrics. We also plan to integrate our design on FPGA with integrated RF data converters, ADC and DACs on the RF SoC platform for an end-to-end JRC transceiver prototype. Thank you.